This is good? All right, thank you. Okay, welcome back, I hope. You guys are back to this AI series by a Center for Career and Professional Development, right? Yes. And my name is Yutaka Takiura. I'm a professor in a design management program. And I'm an architect, interior designer, but teaching design management. And back there from CCPD, Deborah Yanagisawa, and she and I worked on this, and Kathleen Chen, she's a student upstairs and who is helping this organizing this program. And first, before going to introduce tonight's amazing speaker, tonight is a second night of 4-night series. And this is about a amplified future of human creativity, correct? Yes. And then Toru Hasegawa, I'm going to introduce you very quickly soon. And next week, AI through a lens, and another friend of mine and a couple others will talk about music and so on. So please come back. And in 2 weeks, a human emotion and the machine by Natalie, right there. She will come back and give us a talk about what human emotion and machine. And well, I have no idea, so that's so exciting. So you should come back. All right. So before going too far, tonight we will listen to Toru Hasegawa, and he has a couple hats, and he's a good friend of mine, and he's architect, right? I mean, you started as an architect.
Trained as an architect, yes.
Yes.
Practice
that's
too.
one job he's doing. But not only architecture and architect. And my question to you guys is, what is architecture? Right? And then the second question, what is design? And because most of you are here, and Pratt is mostly like an art and design school. And then my question is, what is art? What is design? What is architecture? And is that building? Is that design is just sketches, same thing? Maybe through his presentation, we may learn something, and we can have a conversation after this. And I don't want you to be too formal today. And after his presentation, I want you to ask questions or just have a more dialogue and enjoy the conversation. Then he's a professor, assistant professor at Columbia and Graduate School of Architecture, and the Cloud Lab. He's a co-director at also Graduate School of Architecture, and Columbia University Graduate School of Preservation? Planning and Preservation.
Planning and Preservation.
Yeah, GSAP. And then he is a co-director of Morpholio. That's co-creator of Morpholio. That's a software company. So not only doing architecture design, but you're doing software. So it's cool. It's interesting. And co-director of Proxy. That's a design studio.
Design studio.
Right.
Yes.
So do you guys know what he's doing? So we're gonna find out.
Yeah.
Okay. Thank you. So
All
go
right.
ahead.
Thanks, Yutaka. It's really exciting to be here. I do teach, so it is refreshing to be in a different school. But the topic of AI is really has been booming in the past few years. Are you guys familiar? How familiar? Like, I'm assuming everyone here is in architecture, design, or similar, correct? No one here is in finance or finance, tech. Anyone? So a lot of the stuff ML is doing is coming from that side. But today I'm going to try to wrap it around more our design community that I'm from and you guys are probably from. But just to kind of give you a little background of mine. So Yutaka's already mentioned most of it, but in the academic side, the pedagogy I'm trying to distill, and I've been teaching since '06, so for the past 10 years, is really about rethinking computation. So we do all have these Macs and PCs, and they're extremely powerful, but we don't know what's happening in the box. So it's a forum for me to teach students if they had a software they wanted to make, I help them make them. We rethink what computation is, and really kind of build a computer literacy of what this so-called generalized machine can do. So it could technically do anything. But if you are just running on top of current software, the software is kind of the framework. So that's an area of research I'm doing. Proxy Design Studio is more of a domain of how to apply all this knowledge. So we've done consulting work, we've done fabrication, we've done the whole gamut of how we can use technology to either automate, help your creativity, really kind of do the fabrication in sync with your work, really try to apply it to real world practices and problems. Morpholio has been my work for the past 5-6 years of really diving into software. So this was just right as the first iPhone came out. My partner and I went to buy the iPhone and bought the first Mac that I own. I've also come from the architecture side, so I've owned a PC, super juiced up, super hacked together, and just bought the first Mac because that was the only way you could make an iPhone app. So version 1 of Xcode, horrible, super difficult to even get it starting. But as we learned, what I saw was that the app store was just like the electricity outlet of earlier technology, right? Now none of us can even think about a house without electricity, right? What would you do? Your phone goes, your laptop goes, there's no light, no nothing, no fridge. And the App Store was just this first, when it just came out, we had the same sense. Like it was an outlet, but there was no appliances. So the apps were the new appliances of this, let's say, decade. So this year is iPhone's 10th year, and now we see millions of apps out there, but they've created this outlet for technology that previous was like electrical outlet. And one of the famous scientists at Stanford says about machine learning is kind of the next outlet. It's a new form of technology that is just going to flourish. And we think of outlet no more because a very successful technology just disappears into the back. And just like we don't even question about app stores anymore, this is another form of a successful technology that just disappears. So it's a really interesting way to assess what good or bad, that's not necessarily the importance, but what you would just don't even think about is a very established form of technology. So here we were really saw that as an opportunity, but more so we were really interested in technology that could assist creativity. So at the time when we started, or even currently, there's a lot of AutoCAD, BIM, 3D Max, all rendering related technologies that are really useful for end renderings or fabrication, but doesn't necessarily assist you in the creative domain. So we know, and I know through practice, that design is very messy. So what are software and platforms that could really assist messiness? And that does tie into this discussion about artificial intelligence and machine learning in a bit. So keep that in mind, how our brain works and how design is not a linear thing, it's a non-linear process. And we're trying to make software tools that assist in that form. So anyone here done a kind of course on AI or learned AI? It is kind of a vague name that has kind of been used because it's really cool and it kind of sparks ideas. But the concept can be like very, very messy in what it is because the topic is not fresh. It didn't start last year. It started 50, 60 years ago. So this was around Alan Turing, talking about computation, the Turing test, even the first thoughts about what computers can do, or even the blueprint computers. So it does date back that much. So some people might think it's like pattern recognition. Some people might say it's data mining. Some people might say it's neurocomputing. So everything is a little touching each other. And the recent and most kind of clear way people like to talk about it is AI and ML, which is machine learning. And the really bleeding edge everyone is talking about now is deep learning. So this is what you might have seen from Google, et cetera, and we can break that down a little bit. But just to get everyone's mind around like what is AI, artificial intelligence is trying to distill a way to understand something, right? So it's just a form of comprehension and the ways in which it can do it. So here's just a fun clip. You guys probably watched this movie.
Do you know what the Turing test is?
Let me play that again.
Do you know what the Turing test is?
Yeah, I know what the Turing test is. It's when a human interacts with a computer. And if the human doesn't know they're interacting with a computer, the test is passed.
And what does a pass tell us?
That the computer has artificial intelligence. Are you building an AI?
I've already built one.
So the Turing test was made 50, 60 years ago by Alan Turing. And this was a start of a way to really model intelligence that was very different. So, and how I can explain it the best is through my experience through programming as well. So programming or writing software, whichever way you want to talk about it, was really architecting how to make decisions, and it had an expertise of, say you wanted to understand what a cat looked like or a hot dog in terms of modern media, is you would say, well, the cat is furry, it has 4 legs, it might have some whiskers. Like an expert will try to write out a lot of the details of what it is. So the programming was, here are the inputs, here's this expert program that ran, and it told you it was a cat or not. Machine learning is almost the opposite, and this is relating to Turing tests, is because Turing has established that it doesn't matter how we understand intelligence is, if the system can overcome the acknowledgement that it's a computer or not, has already passed the intelligence problem. And how machine learning algorithms are made is pretty much that way as well. Is you have there's several series. I'm kind of really breaking it down to a very generic way, but you put inputs and outputs in other ways. You can have 1 million photos of cats, and that's the input, and the output is these are all cats. And you can also have images that are not cats. The computer takes it and gives you a program that will tell you it's a cat or not. So the program is, there's a black science to making the training set. So this is more technical, but just as an image, just put in your head that before the previous paradigm, and I've been in that paradigm too, and currently in, is you write programs that you take input and that you design the output. But that has kind of reversed on its head in the sense that the computer gives you back the program that could determine at a pretty good accuracy if it's a cat or not. And that comes back again to that Turing test, is they're not worrying about how you define a cat. As long as it can detect the cat, you're pretty much all good. So this is the project Google released last year in their blog. This was the Google research blog on supercharging style trend or transfer. And what they've done is they've trended all these, let's say, styles. So you got Van Gogh, you have Miro, you have Ukiyo, I'm forgetting some of these. But what he is doing right here in front of you is just mixing that blend. And the more evolved version is from this year's SIGGRAPH. If you guys want to see the bleeding edge of a lot of this, you just go check out SIGGRAPH and they'll just show you all the papers published. But this one is even more interesting in the sense that here's a style, the machine has learned it, and it's already applying it. Let me just wind back a little. Here's the original video of that person's face, and just applying these styles on top of that video real time. So previously, this would have been impossible, if not wouldn't know where to start it. But it's coming to that point that style can be learned. And there's always a question of who makes the styles or what it is. But just from the previous example of Google mixing style, it's a whole new generation of style, right? Before, when remix just came into the picture in music, people were like, remix is not music. But look now, our world has flourished with remix music. So there's a current status of design that's being kind of held to the challenge of like, are we style makers? And if that is the answer of your definition of an architect or a designer, there is some big waves coming in the next couple of years. Another project that I really like from this year's SIGGRAPH is this project of modeling. So we all model in the school with 3D Max or Rhino or Grasshopper or whatever form of input, right? So again, like the traditional way has always been, here's your input, here's how we process it, and here's how we manipulate the end result. The input here is just a sketch. So the deep learning or machine learning behind this tool has learned how to understand a sketching input to model a 3D model. So you've kind of bypassed even the whole process of trying to model. So again, machine learning is really putting a lot of stuff on top of its head. It's reversing a lot. It's like, you don't need the expertise, you need the idea or however input you want to be as most intuitive at the forefront. This one is maybe a little bit out of context for some, but if you are familiar with character animation such as this, and I'm sure most of you here in the school have used Maya Max, which is used for that, and know that these key motion animation is done through captures. So you would have someone running and someone jumping and someone, let's say, throwing something or falling. Those are very discrete moments. What this is doing, and in particular, we'll skip how the implementation is it's understanding whatever input it has to understand the context of its movement. So it's blending pretty much in situ what it could be. So there is no more, here's a jump. If you're a gamer, I don't know how many of you guys are, if you press A and jumps, there is an action designed just for that jump. And if you want to push forward, you run. Or if you push sideways, you walk sideways. Those were very traditional programs. Like, here's the input and here's what it should do. Versus here, the input is just go left or right. The program that understands those inputs and the context will actually then figure out what it should be doing or guessing the best alternative motion it should be doing. So there's no, here's the button equals X. It's pretty much a more comprehensive way of moving like we would do, like in situ. So if you look at the movement of this character, I mean, it's beyond me in the sense that that's probably how someone would really walk those terrains. And these terrains for machine learning is unknown. Like the inputs are coming in as unknown variables, but it would find the very best solutions to its context. Now, I don't want to get into too much of these projects because they're super exciting. Just another one that's around AR, Apple's new release on machine learning is this kind of augmented reality detecting and applying Sudoku. I mean, that would take me probably a week, like to even look at a Sudoku and figure it out. There's questions of like, well, machines don't have pleasure, blah, 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 whatever. But it's kind of fascinating or eye-opening, right? Like, it's just like instant solving. That's what computers are good for. Some of the work I'm doing for Trace is around this detection of planes. And this is a case where we're detecting the kitchen cabinet or kitchen counter. We're drawing these elements. But the key is that once these scenes are detected, we could kind of relive our sketches rather than going back to a model or sketch your drawings to a 3D model, then model it, and maybe go around your 3D model, just do it on situ. So a lot of this is allowed to be able to do because machine learning does make you think very differently about how you approach these problems. Let me just skip some of these just because this is like kind of the process of capturing the grid. So these detections are pretty sophisticated now, so you could know when one thing is 1 foot, 3 foot, whatever dimension, it's to scale. So once you capture a grid, the scales are captured as you're finding out what angle of camera and etc. and you just sketch. So when you send that sketch to your client, that is like a 3 foot by 10 foot pool, and it's already known. You don't have to go into a CAD to measure it and draw it. So a lot of this intelligence is just going to be right there and then, already in play, and if not, even more intelligent. Some of the fun one for interior designers is kind of just sampling. Previously, like color sampling was you carried those crazy books of colors and went on site. This is trying to just extract color from site, seeing the lighting. So these cameras are very smart now to know the lighting qualities of the room. So like we're changing from cubes to squares to assess the lighting quality for a specific color in situ, and we're propagating some knowledge of what color should be a companion for the product you're looking at. So that's a quick tour of what's happening out there, what's machine learning, what's AI, what's really the paradigm shift that has happened. But it's actually very critical for us to step back and see the whole trajectory of technology. So AI and ML is kind of the forefront, but I do talk about these three things to kind of give you some context and the trajectory of what was and to come through these three stories. How many of you play chess? Anyone? So do you guys heard of Centaur chess? Centaur chess is pretty fun. Like I don't do it because I don't have the time to do it, but this was when Garry Kasparov lost against the Deep Blue in '97. Everyone was super excited about those story news, and it winded down because he lost, but funny enough, he continued to evolve the thought, and this is where it's really exciting, and this is created by Garry Kasparov himself, was he set a tournament of free-for-all. Anything could be game. So you could bring your supercomputer, you can bring 10 supercomputers if you could, you can bring 100 people if you wanted to, you can bring your dog. Whatever choice you wanted to play the game was all fair. And of course the tournament goes, and the cut to the chase, any guess who won? Who won? Like, it wasn't a supercomputer, first of all. That was a big discovery because he just lost against the supercomputer. But the end tournament was a group of highly ranked chess masters. There's a whole ranking system. And they're juiced and sponsored just computers for chess machines to assist them. And the opponent were two amateur American chess players with their amateur-made computers. Guess who won? No guesses. You guys need to talk a little more. But it was the amateur team, funny enough. And that's the excitement of this tournament, is it's not about speed, it's not about crazy powers. There was this synergy about computers and humans that would add up to become more. So this is one point for you guys to take away today is, yes, everything is accelerating, it's super fast, the guy with the fastest car is going to win. Actually not. You have to kind of take that in, is somehow you as a designer in combination with a computer is very different. So that's something to know through this. Like, this was just the proof of concept of that. And again, this race against the machine is kind of not new either, right? Like the first industrial revolution in the 1800s. There was the whole, Luddites who wanted to destroy mills because they were taking off jobs, whatever. But funny enough, there was this legend of John Henry against the steam engine. So it was who could drill faster, right? This buff guy, drill, or hammer through rocks against a steam drill. He won, but he died because his heart exploded. So that was kind of when human power has lost against the machine. And again, the Manhattan Project up, in Manhattan 50 years ago, when they were calculating the atomic bombs sequence, at the time, computers were actual humans. Just like you call someone a runner or a painter, right? A computer was someone who calculated. And there were obviously everyone, running out of time. There was this race, like it was just the first few years where these mainframe computers started to get close to a computer, human computers calculating. And it was also a race, like who could calculate first? And the first few calculations, the humans won because they're fast, but they had to sleep, they had to eat, they had to rest. And in the long run, the mainframe started to beat the calculation speed. And again, Garry Kasparov, in a very highly intellectual game of chess, lost in '97. But just to say that this has been just one trend of technology, is that what we used to do, so lifting stones or drilling holes, has been replaced, thinking has been replaced, and so forth. Another story of computer literacy is an interesting one, especially for you guys or the generation post-2000, is the early era of computer. You literally made it in your garage, right? Like Steve Jobs or Bill Gates, or even before that, Intel or any of these guys. Our computers that we're surrounded with, your iPhone, your iMac, your PC, they're so sophisticated. It has generated this generation of people who can't hack computers because they're too expensive. Like, kids can't break a computer, your dad's $3,000 computer, because it's too expensive. And this computer scientist named Evan Upton from the University of Cambridge was really shocked when these students that were coming in did not even hack together much stuff. Like, the most they've done was maybe put a Facebook script or whatnot. And it was because of this context of not a hackable environment. And he made this $25 computer from that experience, that there needs to be more, let's say, material to be playing around with to even come to the next innovation. And there is kind of a question of how the innovation gap may appear in these generational gaps of non-hacking bodies of human, but in the context of computation, like we do Facebook, we do internet search all the time, but we don't consider what's behind it, of kind of breaking it together, is some context that's appearing. This is a chart from Singularity is Near. If you've read Ray Kurzweil, you probably know this chart. But this is a logarithmic chart of evolution of technology in a long span of time. The middle chart is a logarithmic time, so it looks like a linear graph, but if you truly mapped it out in time, it's the far right. You see how the most modern evolution of technology has just happened in only the past few hundred years. And this is from start. So this is just to talk about his point of technology evolution as acceleration will only be faster. So right now we're like, oh, there's amazing technology coming out. In a few years' time, if not a few decades, that acceleration is going to be faster. And from his funny joke about the matter of human minds are a linear program. So when we were in the Sahara trying to hit an arrow on a deer, that's a linear problem, right? That deer is going to be right there. I'm going to throw it right there, and if I can hit it. And we don't have the capacity biologically in a kind of framework to think in an exponential way. So these are a problem he's addressing in terms of how technology and the evolution of it were mostly blindsided of like what's behind that accelerated need. Just the context of like what our relationship to machine has been. Again, in the 60s, you had to share a computer, right? You had to share maybe 10 hours out of a section of a week with 10 people. 80s, your first personal computer became a one-to-one relationship. Now everyone in this room probably has an iPhone, iWatch, a Mac, a PC, maybe even a PC at home. Like that is growing, right? And that is going towards the direction of just more devices, more computation in the cloud. And these are part of why the machine learning AI stuff is seeing a new light again, even though it was started 50 years ago, is because the internet brought mass data, just tons of data to even use as a training set. And then the computational speed of the Moore's law, you all know, has allowed to be able to crunch on that data. Otherwise, it would have still remained as a theoretical exercise. So again, just to summarize that flow, human sweat through IR became amplified, like our sweat. Now we can make skyscrapers, we can make cities. Like, you don't do that with your bare hands, but through machines. Personal computers, now we can compute stuff, think beyond what we can think, simulate. A lot of that power has been given to us. Human speech is a product of the internet. Now your voice is heard all around the world if it could. These sensor devices are really changing how we behave. So behavior is kind of being amplified through these mobile technologies. And this line is just continuous, right? And ML, AI stuff is probably, again, somewhat, I think, is addressing human identity. It's like who you are as a human, what is to be intelligent and be creative. Interesting enough, garbage in, garbage out, like if there's not something to amplify, there's really just noise. But every signal is kind of coming through the human, which is kind of the interesting part. And the last of these inputs is this creativity. There's some flashes. I'll just ignore. A little too loud for continuing. Fire drill.
Okay. Technology. Yeah, technology.
Sign candidates. But that was more in the context of a specific studio. But just to kind of give their system, what they had was, it was a DARPA grant that was given to the professor Paul Sajda. He was one of our connections, and David Jangwa was his student. Was to assess, it was a grant to assess a large data set that the military was gathering over these drones over Afghanistan or wherever they were surveying. They had 24 years worth of data, video data, and they had to quickly assess what was to be highlighted. And they coupled the brain and the visual data to be synchronized. So they flash 5 to 10 images a second and will detect important hotspots. So they were looking for example, tracks or camps or trucks or missile-looking images in this data set. And it would highlight this ginormous data set that would have been impossible through computer vision and impossible through human vision. But we took that kind of further, and there's all these values that we know what our brain is telling us through kind of the data analysis of the signal. So when everyone's sleeping, it's usually alpha, it's more calm, relaxed. And when you're more attentive or focused, you have very short waves, like high frequency waves coming out of your brain. And it's obviously known if you have both at the same time, it's like a seizure or it's something medically not good. So there's all these parameters that we know through that. And the first was quite simple. We wrote an application that we wanted to track the subject, record the brainwave with one sensor electrode, and gather the data to see what this was about. And this is a kind of quick video of we're plotting these, let's say, signals that we were gathering from the passage. So the black line to white line is where the subject walked, and we're projecting these attention values and meditation values that our signal was processed. And it was our first experiment to understand, like, can we really understand space more from how the human body is sensing the space? So all our metrics around architecture has been more external, like how tall, how wide, how big, what are the measurements of heat gain, what are the measurements of wind flow. Those are very external metrics of space. But we wanted to take that from the human perspective, like what is the human body perceiving? How is the brain perceiving space? And that was trying to establish another framework to measure space from a kind of sensory standpoint. The version 2 we've done was sponsored through Van Allen Institute, and we ran it through Dumbo. The difference was we had more subjects. We ran it through 50 subjects of the same experiment. This led to larger samples, so not just one data set per path, but many data sets per path. So this is part of the machine learning data analysis. All these signal processing is more about, there's ways and techniques. So this was a technique to have more samples to gather that you can start to weed out noise of different parameters. Interesting enough, and some were more obvious, maybe discoveries, but where there were crossroads or where your crossings is higher tensions of, you will see red crosses versus narrow corridors with more meditative values. So the one that I did this summer in Seoul was version 3. Now this is again sponsored through the city of Seoul. Better equipment, running different sites in Seoul is the same experiment but with a higher density of electrodes. So previously we were just sensing one electrode. This time around we were sensing 8 to 16 electrodes. These hardware is called OpenBCI. It's a company here in New York. And we were walking through the city of Seoul to detect these different sites. So one was at, the Zaha Hadid's, I forget the name of the museum. And these were the sites that we were walking around and sampling. So you can imagine us going to these different sites, recording the brainwave data, and gathering all this data. So just the process to see, you kind of have to fit it well. It's you had these kind of notches to adjust per head. Interesting enough, Asian heads are different from Caucasian heads, like in the kind of dimensional properties. So it was kind of a measurement that we were also surveying for the OpenBCI company. But that's what a signal typically looks like that's coming out. Again, it's a low frequency, so it's 0 through 60 hertz that you're gathering. Obviously, if you kind of blink or bite your jaw, all these muscle electricity is much stronger than the actual brainwave data. So we had a process, and we also gathered all this 360 camera. This is just a footage from the 360 camera for later analysis of even trying to compare real spatial data versus, say, you had a VR headset and EEG recording to see if there's a comparative difference. But just to cut to the chase, since we don't have that much time, these were the things we were comparing for sites. It's called the big three. So you have alpha, beta, theta, low gamma, which are more meditative values versus more attention values in rough kind of comparison. And we were sampling these different sites. So the premise is very simple, like recorded these different environments. So ones were from a kind of peak of a site that was looking down to the city. One was on top of the Zaha Hadid Museum. One was underground with no natural light. And another one was a kind of high crossroad. And this is just going through how we process the raw data to filter. Technically, this is technical stuff that's not necessary for our talk today. But the interesting part is this neurotopograph map. So this is giving that same map based on the brainwave data. So where you're seeing higher elevated, for example, this map to the right of the map, that zone where it's high in red is where it had the most alpha waves amongst all the site, and the lowest was the one that was like an underground passage we were recording. So simply put, it might be some things that we obviously know, but like where you have a higher viewpoint, more greenery versus underground, enclosed, artificial light, obviously emits different values in the brain. So how this could be interesting, at least in this context of artificial intelligence and AI, is that we don't have to an extent, just like the paradigm shift in programming, rather than an expert trying to formulate some algorithm in programming to understand space, we could take it from all this data. So we could take all this data gathered through EEG to do a kind of a categorization of space from the data we can assimilate to program how we analyze new environments, or design for that matter. So just to kind of summarize the talk, so there are three things, not just in relation to machine learning or AI, but just how technology is kind of redomaining things. So as much as we think Kodak as a company that is gone now, but Instagram is still a kind of photography filter or existence, is a kind of shift that the simplest analogy is like you had propeller engines, but we shifted to a jet engine. And the next engine could be some other new electricity-based motor. It's still an airplane. Like, technology can shift under your kind of your hood, but shifts kind of radically our social structure to an extent. Technology becoming more biological. So this is somewhere how these data, or how we analyze, the machine learning, deep learning is a model from our brain. It's taking the neurological structure, how we think is operating, and taking that model. And not only is it happening at the software level, but it's also happening at the hardware level. So this is Amazon's far-fetched version of delivery, is that it's this flying bird that will deliver your thing. So that's also something that's happening very fast. And this is a question that is part of similar to what Yutaka is trying to ask everyone. It's like, what is architecture? What is human? Is related, is the definition is a constant target. It's not defined. And this is part of the middle guy. His name is Hiroshi Shiguro. He's a professor at Osaka University. His mission, he's a roboticist, but his inquiries are very philosophical. It's like, if you externalize all human function, what remains would be what is human. And he's made a Geminoid, that's his project, a complete replica of himself that looks like him. So he's doing an Turing test of robotics. So what is the point where you can't tell the android, this is really sounds like sci-fi, but this is actual research. Like, what is a robotic construct that will pass that robotic Turing test to an extent? And he said he's at a 30-minute point. Like, he's put his android in a cafe, and it took 30 minutes to someone to identify it was a robot. So it's an interesting inquiry that's just going to, again, exponentially grow, right? It's going to be an hour next year, 10 hours next year, 100 hours next year, and then, funny enough, we won't know if I'm an android. I'm actually an android standing in front of you guys. I'm just beaming in from my bedroom right now. So, and my last anecdote to this is, all these things of evolution and technology has a very interesting connection. It's like there's never here, this leads to this leads to this. And the really great example is the steam engine and the steel road. So before they both met to make the train, the imaginable steam train, is that the steel rail was existent. These horses were pulling carriages, and it was only like 100 years later someone thought, well, you know, we could put a steam engine on top of it and see if it runs. And that was kind of how they met. And it just is a kind of point that technology, you never know what comes and what combines, and that's a little the difference between biological evolution and technological evolution that is currently happening. Thank you.
I have a question. I think that the way you explain machine learning is very interesting. So actually, the computer takes in input, output, and gives a program, right? So I'm interested in how the computer can output a program. I mean, you need a program for it to output the program, right? Is that clear?
It's super technical, so I don't want to get too technical about it. I definitely recommend what's the name? It's Andrew Nag. He's a professor at Stanford. He has an online course called Machine Learning, and it's on Coursera. I think you could take the first few lectures for free, and it will show you how that algorithm operates. So what you're asking is like, how is it done in the background? Like I just showed you the diagram. So it's pretty straightforward. Like you can understand almost, here's how it takes these pixels and then tries to make a feature, like feature detection, and then it runs through convolution, and it's very technical. I can't explain it to you in like 2 minutes, so definitely take advantage of those resources because there's plenty of how to machine learn. So that's all out there right now, and it's very available.
Thank you.
Hi. So, I mean, my question could make sense and it might not make sense, but I'm just curious. So you did talk about brainwave frequency. You know, most of the stage that you experiment is alertness. People actually awake and people aware of the experiment. So these, let's say the people that already know these incidents, could that be changed the effect? Let's say if they falling asleep in their pattern and there's sleeping, the frequency changed nightmare, for example, the people with disability, for example, people who cannot see. So if this experiment are tested on them, we're receiving a different set of kind of experiment. And how does that play into, it doesn't really cater to everyone because you're looking for a certain category of people that you want to get the result from. It doesn't really fit the big populations. Mm-hmm. So it's the result itself is not really generic. Like I wouldn't say it was
right. I mean, it's a totally valid question because we also have, you know, guidelines of how some subject is being recorded. It's very specific. So you're right, and this is coming from our understanding of the technology and how we need to survey the data. We obviously talk with the neuroscientists to guide us through that, because if it's just a thought and we want to record, it's mostly garbage data, to be honest. And to your question about how different people have different pattern based on their physiology is a good one. And even another interesting one is about expertise. Like as an architect, you know space better, for example, or as a doctor, you know about how your body works, right? Those things do matter. So even the fact that you're presented with the EEG data in front of your eyes can already affect the data that you're thinking, right? Because you're seeing yourself in a mirror to an extent. So there's all these issues that are around how you collect the data. We're obviously trying to figure out that as we go, because this EEG, it's called EEG in the wild, which means most EEG data is gathered in a hospital, very limited context of like there's these rooms that are protected with lead walls to not have, you know, radiation from the world affect the data. So there's a lot of that. But as architects, we were thinking that that architecture itself will affect the data, right? Like being in a box is not spatially at all what you would experience here or outside. So taking it out is this kind of next frontier in that EEG research that we're part of as well. So to cut to the chase, there's no right answer yet. There's no known way to establish it. But what's exciting about artificial intelligence and machine learning is that you could almost discard all that too. Like you could just gather the data. The computer can make sense of how you could categorize. So there's two types of machine learning, the kind of controlled one and the non-controlled. I'm missing the terminology. But the ones that are like Google searches, they don't have any end goal. They kind of categorize with what they see. Just they take the world noise and figure out a pattern. And it could probably be done in this context of EEG data as well. And then we could maybe even find correlation that someone who's blind is actually similar to dreaming. I'm just hypothesizing that. But those connections could be made without the expertise. Like, we don't have to make a theory about it, but the theory will be discovered.
So let's say, for example, like the experiment is conducted right now, all the data analyzing that you collected somehow being translated into, almost retranslate into AI, and then AI itself will create a program for, it might be like a little bit way futuristic, like dream recording, dream wave, re-identify dream wave. Like now, let's say we wanted to record dream, we go to sleep, we go into different kind of, sleep pattern. But if AI itself already have these kind of, system data that it said, okay, I'm blinking, this is my frequency, I'm in shock, this is my frequency, let me reanalyze, and I can actually create a dream based on these data analysis that have experience. So does it, like, because in a way, your experiment really, like, I think in a lot of way for me, it's like I feel intrigued because it's give you this kind of mindset that's like, wow, it's, you can wear that, you can actually put thought to it, it's actually analyzing data, but the AI itself can do the reverse. It's getting you information, programming, and give you the data so that when you're dreaming, it's go the opposite. You can create your own dream based on the data that's given to you. Am I confusing you, or?
I think you're designing a design tool to an extent, and I think that's fair to think about it. But just think of what the program that machine learning spits out has a training set, right? And what you can do once that's out is you can take then any other data, pipe it through it, and it'll give you a result what it could be. It could tell you that. So like the very simple example is the hot dog, right? Or the cat. You have a machine learned algorithm that can detect a cat. You can throw in any image and it'll say, it's a cat, it's not, it's a cat, with any data. That's the thing, is like, it doesn't matter what data comes in, it will know how to process. Before it was very structured that it would probably be wrong most of the time because it was only so specifically designed to program to output. So in that sense, that's the learning that then we can take any form of EEG data and we can say it's more about dreaming or it's more about walking or exercising, and we'll know that without having that knowledge of what it is to exercise as a pattern. So that your inquiry of like how to use that, yeah, the sky's the limit, like what to use it for.
Thank you.
So you talk about a lot of how now artificial intelligence can understand the space and art and design. So since computer can do so much, and there are a lot of things like in design that's related to math and science, like the racial and even like the color. Now like computers can recognize them. What do you think like artificial intelligence, like human intelligence and artificial intelligence is different? Like, will artificial intelligence one day become the same as human intelligence, specifically in like design or art part?
It's a good question. How do you compare the two, and what's the analogy to it? Currently, it's black boxed and it's kind of a one-off. So you build it, and it's a very good program to say yes or no to something, right? In a very fundamental way. What's happening now is, well, what if you make that circular in the sense of how you even machine learn something new could learn even better way to make itself. That's where all these people are freaking out about the kind of apocalypse of like machine AI taking over the world. Is once you close the loop of, if we know how to make something, we evolve the next step, right? But what if that process itself can reflect itself? So it's almost like a machine that makes a better machine of itself, right? Like that process is obviously possible to an extent, theoretically, currently, but that's an infinite loop. Like they're saying, well, once you set that into motion, it will come up with technologies that we can't even comprehend, and it's even better, is the kind of warning they're trying to give, you know, all these institutions, etc., that it can come with its own objective. The best way I've understand it is, if a machine has an objective, a simple objective, and this was from, I forget the author, but say the objective was to make everyone smile in this room. Now the human way is like, find a really good joke. A machine solution of optimizing that problem could be putting electrodes in your faces and making you smile, right? Like, it's obviously not a humane, moral objective to find that function, but a machine would do that because there's no moral compass in it, right? So that's where people are kind of speculating these issues, that unless you embed in a hard-coded way into that structure, it's quite dangerous, right? Like, there's no compass in that algorithm. So I don't know if that answered your question, but that's where, you know, my understanding, the difference between human thinking and machine learning. Machine learning, or the AI itself, is kind of a externalized way of understanding some a bit of intelligence. So like detecting a cat or not, it's a bit of intelligence we have that we can do, externalized. But if you had to ask moral questions and judgments, that's another big domain that, you know, is different from our brain, because we have some social structure that stops certain things, right? So we would never optimize that way, but a machine could do that. That's the difference.
But do you still think like machine can do design, like for example, like advertisement design based on the data from the society and from the product, or like from the data that it has? Can it optimize a design?
So you're asking a pretty big question of how you define design. So like the design at a level of rules, let's say, like zoning, for example. It's, you know, some could say it's gray, like there's all ways of kind of figuring out things, but to an extent, it's a finite domain. So when I say finite, the example of a chessboard is simple. There's however many chess grids, and there's however many pieces, and there's however many rules, right? It's 10 to the powers of, you know, crazy numbers that we would never play at all, but it's finite. And you can say that the design is just a matter of looking for one of them in the gazillion, right? But it's finite. So if you had some crazy super fast computer, you can process all of them. It still remains, which one do you choose, right? That's kind of a design process. So to your question, like, can a machine design? Absolutely. Like, it's, if that's your definition of design. But if you're asking more, okay, well, make the next Britney Spears or J-Lo or whatever like music you want to reference as a pop hit. Now that's a domain that's more complex, right? Like, what is music that's kind of will hit more than 1 billion people? That's a criterion of a design that is probably very difficult to figure out. But again, like, maybe there is, who knows? Because again, if you take the notes of a piano, it's finite, right? If you say there's finite amount of code or rules, there is a finite set of music.
Thank you.
So this question goes off of the earlier question and what you were talking about, a machine can do style, a machine can learn style. So for the designers and architects in the room, what would be your advice of what skills they would need going forward to be in a world with artificial intelligence working next to them or with them?
It's a great question because there is the kind of current pedagogy of training the next generation designer about styles or let's say formal, let's say variation, etc., which a lot of it can be learned now. So, but going back to that example of the centaur chess, the end of the match was not a supercomputer. That's kind of the interesting thing to take away, is that it's not the fastest that will win, but the combination of the human and the machine is the ultimate game. And it doesn't matter if the human is not an expert, but a novice. It kind of showed in that tournament. So my recommendation is that the computational literacy, even at a fundamental level, is kind of a critical ingredient in the way you think. The way we think has just shifted drastically, right? It's not just our biological brain. I even add to that, the hand actually is a really second brain that we should use more. But somehow we kind of become this, right? Like we just type. It's a very different way of thinking. But to really rethink how to think is the kind of guiding question for you guys in thinking, rather than just trying to find a solution, right? The way to think through the problem is, it's actually unknown. Like it's all these things that I presented, they're not even 50 years old. They're not even 25 years old. It's so recent. And again, going back to that exponential curve, it's a different way of designing is being set in front of us. That's the best way I can answer that question. Thank you guys. Yeah.